oxygen and about 10% water and 6% oxygen. Okay, and then you capture CO2 here and you generate and you just repeat the process. Okay. Again, the goal that DOE has set for this project is, again, the minimum CO2 capture is 90%. Okay, CO2 capture. And the maximum increase in cost of electricity. That is to say, and if you compare cost of electricity without capture versus with capture, they require only less than 35%. However, thermodynamically, minimum 50% COE is required. Okay, so we have a narrow window to work with. These are basically, technology available. Okay, the cost of reduction benefit versus time to commercialization. Okay, for instance, amine-based scrubbing technology, which I'm going to talk about in a minute, is ready now. Okay, the problem is that the cost is not really good. Cost reduction is not that good. However, if you take a look at the chemical looping or biological processes, benefit is great, but the technologies are not ready yet.
What is chemical looping?
Chemical looping is you loop, I'm not the expert here, but the idea is you have a metal oxide, okay, and then you basically whip the oxygen from metal oxide and use that oxygen to burn the fuel, and then you form a metal. You basically use metal oxide to form a metal, and then you oxidize it. Okay. So that technology has benefit in terms of reducing the cost of capture. But the problem is that now you have a huge amount of solid oxide particles to deal with. Okay, so that's not easy problem, because if you take a look at how much CO2 that you generate from say 500 megawatt typical coal-fired power plant, it's enormous. Okay. So still, it's a long shot, but there are a couple of projects funded by ARPA-E that appear to be promising as well. So this is a typical amine adsorption process. Again, this is the current state of the art. Okay, it turns out that this is the only technology that can be potentially deployable if you have to. Okay, so the idea is you have amine. Amine will chemically react with the CO2 in the presence of water, and you form carbonate ion here. Okay, so now this reaction is reversible. If you heat it up, then the amine will liberate CO2. I'm not going to go into detail here, but the promises of this technology is the fact that this technology is mature. Okay, originally developed to get food grade CO2. Okay. When you drink soda, you have CO2 inside the soda. Those CO2s are coming from this amine-based, scrubbing process. Okay, and it turns out that currently this is the only large-scale technology deployable, which means if you don't care about the cost, then we can build a plant, and we know how to do it. Not me, but they know how to do it. Okay, challenges. Okay, when a capture and compression system is added, the plant's overall thermal efficiency drops from about 20% to 30%. Okay, 24% decrease. This is due to the parasitic energy load from the CCS system, and the majority of the expense is incurred during regeneration. Okay, the reason is simply because we have large volume of the solution must be heated to about 110 Celsius in order to liberate CO2. Now, it turns out that 60% of the solution is water. Okay, water has high heat capacity, which means in order to increase temperature of the water, you have to provide a lot of thermal energy. Okay, so people are trying to use, say, ionic liquid instead of amine, where you have like 100% ionic liquid, there's no water. Okay, so that's also the project that supported by ARPA-E as well. Amine-containing solutions are generally viscous and corrosive. Viscous means it's hard to deal with. Corrosive means it's you have to have a special containers, reactors, in order to contain this amine. Okay, so these are challenges. If you take a look at the other technologies that are available, potentially, solid solvents and membrane-based technology. Okay? So these are basically the technology that we have proposed, and obviously these are not new technology, but we have a sort of new materials that we proposed to address all the challenges that these technologies have right now. So solid solvents generally require lower regeneration energy, okay, as compared to absorption. Okay, physiosorption requires lower energy than chemisorption. Again, physiosorption is basically gas molecules is absorbed on the surface of solid particle, Van der Waals by Van der Waals interaction. Okay, and chemisorption is basically gas molecules absorbed on the solid surface chemically, so chemical bonding. Okay, so as you might imagine, physiosorption requires a lot lower energy. Okay, typically Van der Waals interaction is about 1/20 of covalent interaction. So carbon hydrogen bonding is about 100 kilocalorie per mole, and hydrogen bonding is about 5 kilocalorie per mole. So in order to dissolve gas molecules from the surface, if the gas molecule is absorbed due to Van der Waals interaction, then you only need to provide 5 kilojoule per mole of CO2. However, chemisorption, you have to provide 100 kilojoule per mole. Okay? However, chemisorption has much higher CO2 active selectivity. You see, pros and cons. Okay? Chemisorption, huge, because only CO2 will react. But then bondings are too strong. Physiosorption, bondings are not too strong, so it's easy to regenerate. However, selectivity is not as good as high as chemisorption. Solid solvents are really safe for local environment and are easy to deal with generally. And membrane technologies at the same time require low energy, again safe for local environment, low maintenance, and easy scale up. Which I'm going to talk a little about this in a minute. Okay. Now, gas separations. One can achieve gas separations by two unit operations. One is adsorption and the membranes. Okay. Adsorption is separation achieved on solubilities, okay, thermodynamic affinity. The idea is if you have a solid particle, if you have two gas molecules, which one thermodynamically, which one preferentially absorb on the solid surface? Okay, so that's based on that you can design, in general, design a solid particles that have a specific interaction with specific gas molecules. So you are basically separating the gas molecules based on thermodynamics, okay. Enthalpy of adsorption change. And the cyclic operation, adsorption and desorption required, and relatively large scale can be possible. So the selectivity of, in this case, gas molecule A and B are proportional to the solubility of species A divided by solubility of species B. However, in membrane-based separations, okay, separations are based on both solubilities and diffusivities. Okay, solubilities again thermodynamic parameter. Diffusivities are kinetic parameters. Okay, diffusivity is basically how fast this gas molecule can go through. Okay, this porous structure or polymer structure. Okay, this is polymer membrane. They can play a role. Continuous operation is possible. Okay, and there's no moving part in general. Low maintenance cost can be achieved. Okay. So again, so selectivity in membrane separations, you have thermodynamic based separation as we have with adsorption based separation, but at the same time we also have a diffusion based selectivity. Okay, so we can play with the kinetics and the thermodynamics at the same time or independently, for instance. So now let's talk about stimuli responsive MOPs. Okay, why we think this type of MOPs are exciting. Before we do that, let me just give you a brief idea about what MOPs are. Okay, MOPs are basically metal-organic frameworks. Okay? This is crystalline inorganic hybrids material. Okay? And it has inorganic clusters like this, okay, nodes. And then these nodes are interconnected with this polytropic ligands, linkers. Okay? Imagine that you can put the two oxygen over here, and these two oxygen is basically these two oxygens. Okay? And then you can build like Lego. Okay, when you build a Lego, right, toys, you have stuff, you just build. So, okay, you can imagine this as a sort of solid sponge. Okay, you have sponge, right? You have sponge, and you take sponge and put it into water. What happens? Water will suck into the sponge, just like that. This material has a lot of pores inside, but unlike a sponge, the pores are regular. Okay, if it's a 5 angstrom, then throughout the structure, all 5 angstrom pour. Okay, 1 nanometer, then all 1 nanometer. It could be 1-dimensional, 2-dimensional, 3-dimensional. So imagine this a solid crystalline sponge. Rigid pore structure with the pore diameters from micro to mesoscale. Micro means pore size less than 2 nanometer, and meso means between 2 nanometer to 50 nanometer. And a chemically tailored pore environment. Why? We can put additional functional groups. We can make it acidic. We can make it basic. We can have acidic and basic. Okay, we can introduce a lot of functional groups. Flexible framework displays molecular gating effects or breeding effects. The idea is because now these ligands are organic, it's rather flexible. Okay? So you see interesting phenomena. Chemistry is limitless, question mark here. Okay? Obviously, as long as you design ligands that can attach these clusters, you can build. Just like when you have a Lego or block, you can build, many different things. You can build a house, you can build a castle, you can build cars. In principle. Okay, but that's not that easy, by the way. But I'm not a chemist. I don't have to worry about it.
Okay, I'm sorry, just a clarification. I guess I kind of got a little
Uh-huh.
lost. Do the gases flow through the membrane and then get diverted out the other side, or is the CO2 caught inside the membrane and then the other gases come out?
For absorption, okay, if you have a powder, then CO2 will be just like a sponge. Okay, this is sponge powder. Now CO2 will be selectively absorbed. Once sponge is filled with the CO2 or water, whatever, okay, in this case CO2, then you stop the absorption process and you basically flush the CO2 from the, just like squeeze. That's regeneration. Okay, you just squeeze the sponge and the water will, right, CO2 will, come out from the sponge. In membrane, okay, you are not operating that way. So you have films, and this film is separating, say CO2, CO2 rich side here, okay, feed stream, and then downstream here. And now CO2, now we have a partial pressure gradient, or chemical potential gradient, to be more exact. We have more CO2 on this side and less CO2 on this side. Okay, then there is a continuous driving force for CO2 to be absorbed and then diffused through the sponge and dissolve. Okay, so it's not like you just saturate the membrane with the CO2 and stop the operation and dissolve it. No, that's basically the absorption process. Membrane is continuous process. You continuously absorbing here, and you continuously. Then the question is, you really have to maintain this partial pressure gradient.